Stand at the base of a mature coast redwood, and you are looking up at a living structure that reaches more than 300 feet into the sky. And right at the very top, where those highest needles are catching the morning sun, fresh water is arriving right now. Moving hundreds of gallons of water that high usually requires serious industrial machinery. But that tree has no pump. It has no heart, no motor, and not a single moving part anywhere in its body. So how exactly does a redwood pull water out of the soil and drag it hundreds of feet straight up against gravity every second of every day? The sheer volume of liquid moving vertically through these forests defies our intuitive sense of how mechanical work is done. To figure out how the tree pulls this off, we have to rethink how water actually behaves. The most common guess is that trees just soak the water up. Think of how a paper towel pulls a spill upward. That effect is called capillary action, and it happens because water naturally creeps up the walls of microscopic pipes inside the wood, known as xylem. This diagram compares that capillary climb against the actual height of a redwood. The physics show that capillary action in a tube the size of a xylem pipe runs completely out of energy at exactly 1 meter. It barely makes it past your knee. Since the most obvious biological mechanism fails right at the starting line, a completely counterintuitive, invisible force has to be doing the heavy lifting for the remaining 297 feet. The trick to understanding this is to stop looking at the roots pushing water up from the bottom and start looking at the leaves pulling it from the top. All day long, a tree opens tiny pores on its leaves, called stomata, to breathe in carbon dioxide. But the moment those pores open, the warm, wet water vapor inside simply escapes into the drier air outside. This process is called transpiration. This is where the physics get strange. Water molecules are notoriously sticky. Through tiny electrical attractions called hydrogen bonds, they lock together in a vertical chain. This is cohesion. When a molecule evaporates, it tugs the one behind it, pulling the chain down to the roots. To keep this heavy column from slipping, a second property kicks in, adhesion. The molecules physically grip the walls of the xylem tubes. Together, these forces form the cohesion-tension theory. The water inside a giant tree is not being pushed upward. It is hanging under immense negative pressure, being physically stretched like a solid steel cable without breaking apart. To maintain that massive stretching force, the water needs a reason to keep moving up. Biologists measure this urge using a concept called water potential. It describes the natural tendency of water to flow from a high-energy area to a low-energy area, much like a ball rolling down a hill. Looking at this chart, you can see nature has set up a perfect downward staircase for the water to follow. The damp soil has a very high water potential. Inside the trunk, it steps down to medium. Up in the leaves, it drops even lower. But out here, in the dry air outside the leaf, the potential plummets into the negative, creating an unyielding pull that the water cannot resist. And the thing keeping that air dry and driving the evaporation is just the heat of the sun. The sun is actually doing all the physical work of lifting the liquid. The tree itself spends zero energy in this exchange. It just builds the biological plumbing necessary to exploit the sun's free thermodynamics. But this system has a dangerous vulnerability. The taller the tree grows, the heavier that vertical cable of water becomes. To keep lifting it, the water at the top has to be stretched harder and harder. If that tension gets pushed too far, the water column abruptly snaps. Scientists call this cavitation. The liquid tears apart, spawning a dead air bubble in the center of the pipe that permanently blocks any more water from flowing through it. To protect themselves at extreme heights, the leaves at the very summit are forced to close their pores. They starve themselves of the carbon dioxide they need to grow, plunging themselves into a permanent, self-imposed mild drought just to keep their internal pipes from bursting. Operating a zero-energy pump forces the plant into a brutal tightrope walk. Every hot, windy day is a constant balance between moving enough water to survive and the severe risk of tearing its own veins apart. When you calculate the math behind that tension, you find a hard ceiling for biology itself. Based on the physical limits of stretched water, scientists estimate this hydraulic system will completely fail at a maximum height of around 130 meters. And that is why the tallest living redwoods top out right around 115 meters. They are existing at the absolute physical edge of what biology and physics will allow. Scale that single tree up to an entire forest, and the numbers are staggering. Hundreds of millions of liters of water are being pulled out of the deep soil and exhaled through the canopy every single day. These forests are an active piece of planetary infrastructure. They are constantly pumping groundwater high into the sky, where it can gather into clouds and fall as rain somewhere far away. It is one of the largest and most elegant hydraulic machines on Earth. It operates in total silence, it has no moving parts, and it is powered entirely by the heat of the sun and the stubborn stickiness of water molecules.